Okay, let's learn how to use LOL diagrams to analyze the energy transformations within a system. Okay, so let's start with this. If a system is closed, what that means is that the mechanical energy of the system is conserved. So no energy is going into or out of the system, and all the forces acting within the system are conservative forces, gravity or spring potential energy, that are acting between objects that are part of the system. So let's just look at a very simple example. So we've got a clay ball. You'll see why later on why it's clay, and the earth. That's my system. Clay ball and the earth. Uh, and I want to look at it from the moment the ball is released to just before the ball reaches the ground. So in this case, I have a closed system. Mechanical energy is going to be conserved. I start off, since the Earth is part of my system, I do have gravitational potential energy. I have 100 joules of it, let's say. And so when it reaches the ground, it has 0 joules of gravitational potential energy, but it's all been converted to kinetic energy because gravitation is a conservative force. And my mechanical energy stayed the same. So it's a closed system. So we're going to try to draw this as what's called an LOL diagram. If you just look at it this way, you can see why we call it an LOL diagram, because it looks like LOL. Okay. Now, what this does is we draw first the initial energy of the system in terms of its kinetic energy, gravitational potential, and spring potential energy. That's all we'll do in AP Physics 1. And then we're also going to look at the final energy state of the system in terms of those same three types of energy. And we're going to add another one we'll talk about in a minute, which is the change in its thermal energy. We'll leave that out for right now because it's not going to be part of a closed system, but we'll get to that in just a bit. And then the circle here represents the system itself. So if something is part of the system, if an object is part of the system, I'm going to write its name in here. If there is work being done on or to an object that's outside of the system, I'm going to write the name of that object outside the system with arrows representing energy going either into or out of the system between that object and our system. All right, so let's just try this here, okay? So again, we have this clay ball. It is starting with 100 joules worth of gravitational potential energy. So what I'm going to do is I'm going to, on the initial L, I'm going to make a column of boxes that each represent a given unit of energy. I have 100 units, so I chose to use 20 joule units. So I have five boxes here, 1, 2, 3, 4, 5. Each of them represents 20 joules of energy. And I vary this if I have different, starting energies, but I have 100 joules, so I used 5 boxes, okay? I didn't have any kinetic energy. I didn't have any string potential energy. Now, notice in this case, I'm not writing mechanical energy. You just have to calculate that later if you need to, but that's always shown on an LOL diagram. Now, in the O, I'm going to write the two objects that I'm told are part of the system, the Earth and the clay ball. So any forces, especially conservative forces acting between this, will mean that we have a closed system. And there's no object in this case outside of our system. So our final energy is we have 100 joules of kinetics. So I'm going to write 5 blocks here, each of them equal to 20. Mr. Sampson, we've been doing this. Why are we going through all this effort? Okay, you'll see in a second it's going to get a little bit different. Okay, so what if we did this? What if instead of just letting it go, the person threw it downward and the person applied 80 newtons of force across a distance of half a meter? Well, if you think about that, okay, 80 times 0.5, the person did 40 joules worth of positive work on that object because they pushed it in the same direction that it was moving. So now I want to draw an LOL diagram for this, showing the same two energy states, but except, I'm sorry, at this time, no, I want to show an energy of the system before the person applied the force and when the ball is halfway to the ground. We'll just change the final energy state here, okay? So here we are, before the person even had a chance to apply any force, that object started off, as we saw before, with 100 joules of potential energy. But the person who is outside the system, because the system is still the earth and the clay ball, the person is outside the system. So I draw them outside the circle, and I'm going to draw those 40 units of energy, 2 boxes of 20 joules each, with an arrow pointing them into the system. So I'm saying this person is adding 40 joules worth of energy into the system. It's gaining energy, so it's not a closed system. And then I was told it's halfway to the ground. That means I have half as much of this. So I have uh, 20, 40, and I'm going to just draw a half one here. So I have 20, 40, 50. And then here, I would still have the 50 that it had plus the 40 that was added to it. And now you see that the final energy of the system is greater than the initial. The mechanical energy of the system increased, therefore, it is not a closed system. This is an open system. All right, what about if the opposite happened? Okay, so the clay ball is being dropped, and when it's halfway to the ground, the person does 40 joules worth of negative energy. Well, it's basically the same thing. I started off with 100 joules. Now I'm going to show energy leaving the system. The person did negative work. So basically, energy went into the person's hand and left our system. So I'm going to draw 40 joules of energy leaving our system and going into the person. So now I have 40 joules less energy here. I started off with 100. Now I have 20, 40, and 50. But that's not enough. 25 and 60. Okay, 20, 40, 50, 60. Eric, wake up. Okay. So you see, I have less mechanical energy than I started with. Again, it is an open system. Now let's talk about this thermal energy for a second, because we haven't really talked about it at all this year. The truth is, the first law of thermodynamics tells us that energy can never be created or destroyed. The universe started off with a certain amount in it, and it can get transferred between objects and transformed into other forms, but you cannot create or destroy energy. And so we're going to get a little bit closer to that when we start looking at thermal energy. So thermal energy is just random atomic motion, okay? So basically, imagine this. I have an object that is moving to the right, and it has 100 joules of kinetic energy. Well, basically what that means is every atom in it is moving to the right, and therefore it has 100 joules worth of kinetic energy. And they also have random aspects of the motion, but I'm not representing that. Now, when friction brings it to a stop, let's just say that all of that energy is still present in this object, but now it's present in the random movement of these atoms. So that the random, if they're all moving the same way, that's kinetic, but the kinetic energy of random moving atoms, that's basically makes them hot. When you do this, the friction makes it hot. So that we say it now has 100 joules of thermal energy. Now, this is a non-conservative force. So I now have thermal energy. I don't have any mechanical energy anymore. So although we put thermal energy in our LOL diagrams, it is not mechanical energy. And why? Because it's not recoverable as kinetic energy. There's no way of turning this random atomic motion back into the motion of the object. And it's important to remember that when friction force does work, it produces thermal energy and reduces the mechanical energy of a system. And therefore, if we have friction, it is an open system because energy is going to leave the system. Why is energy going to leave the system? Well, it turns out it is absolutely 100% impossible to keep thermal energy in place. It will always spread away from you. You can't, there's no way you can make a thermos bottle so good that if you put heat energy in it, it doesn't escape. It will always escape. And here's why. I have an object with high thermal energy. Let's say I put it in a vacuum. It's in a magnetic field. It's in outer space. There's nothing touching. Well, here's what's going to happen. Wiggling atoms make infrared light. And that infrared light is going to go off in all directions. And there's no way to stop that from happening. So no matter what I do, those wiggling atoms make light, and that light is energy, and it flows out of the system. So that I'm always going to have objects that are hot. They're going to cool off, always. So energy is going to dissipate from the system. So we often talk about uh, uh, internal energy being dissipated from the system. So a lot of times we refer to thermal energy as internal energy, and it dissipates from the system. So friction force causes energy to be dissipated by turning it into thermal energy. So consider this. Imagine if I had two objects that are of similar mass traveling through outer space, not touching any, no opportunity for friction. They both have 30 joules of kinetic energy, and they're heading straight towards each other. And whack, they hit each other. Before the collision, there was 30 plus 30. There was 60 joules of kinetic energy. Afterwards, whack, there are 0 joules of kinetic energy. But I can't destroy energy. The energy has to still be there. Instead of all the atoms in this object moving to the left and all the atoms in this object moving to the right, now all of the atoms are moving randomly in all kind of different directions. So I have 60 more joules of thermal energy than whatever they started with. That's why I use the delta, because everything is at some temperature. Everything has, unless you're at absolute zero, your atoms are moving and have random kinetic energy. You have thermal internal energy. But in this case, the internal energy increased by 60 joules. And eventually it will cool back down by radiating out into space. So let's just see how this would look in an LOL diagram. So I started off, I had 1, 2, 3, 4, 5. So I'm using 10 joule increments here. I forgot. Okay, so I have 6 boxes here. That's 60 joules, 30 for this one and 30 for this one. And it was all kinetic to start with. Afterwards, I don't have any kinetic energy. there's just two objects in my system, and the Earth isn't one of them, so I don't have any gravitational potential energy. There's not a spring, so I don't have any spring potential energy. I don't have any mechanical energy. My mechanical energy went from 60 joules to 0 joules, but I have 60 joules of internal energy or thermal energy, which is not mechanical energy because there's no way to turn it back into kinetic. All right, well, let's just get a little more sophisticated here. Now I have a box sliding up a rough surface. Remember, when you hear the word rough surface, you need to think friction. You need to think open system. I'm doing work that's going to be producing changes in the thermal energy of an object. So as a box slides up a rough surface, the thermal energy produced by friction is evenly distributed between the box and the surface across which it's sliding. Draw an LOL diagram for this object. Now we got to look. I start off, I had 120 joules worth of kinetic energy and no gravitational potential. So I think I'm using 20s, right? 2, 4, 6, 8, it's 80, 100, 120. So each of these boxes represents 20 joules of energy. Now, I notice at the end, I only have 20 joules of kinetic and I only have 20 joules of potential. All right. Now, that's only 40 joules. So how many joules did I lose? Well, if I had 120 to start with, and I've only got 40 of them left. So that means I lost 80 joules. And I was told that half of them were distributed into the box and half of them into the surface. Now the box is part of our system. So I'm going to put those 40 joules worth of thermal energy that the box absorbed through friction into my LOL diagram here. However, the surface is not part of my system. So I'm going to write ramp surface out here, and I'm going to draw those 40 joules that went into it over here. Now, regardless of whether I include the ramp surface or not, this is still, because there is a non-conservative force, friction, there is going to be a loss of mechanical energy, and so this has to be an open system. All right, let's look at one where there's multiple sources of multiple places where the energy can go. So in this case, we're going to have a closed system. So there's only conservative forces. So my system in this case consists of the Earth, a rock, and a spring. The Earth, a rock, and a spring, and they're all part of the system. So I start off, my object has 100 joules of gravitational potential energy, 2, 4, 20, 40, 60, 80, 100 joules worth of gravitational potential energy. That's how much mechanical energy I have to start with. Now what happens is this has fallen so much that it has 40 joules worth of kinetic and 40 joules worth of spring potential and 20 joules worth of gravitational. So I see I have 20, 40, 20, 40, 20, and no thermal energy was produced because there was only conservative forces. So the mechanical energy I started with is equal to the mechanical energy I ended with. It's a closed system. But what if the spring wasn't part of my system? Okay, so now I put the spring outside my system instead of inside my system. Well, in this case, the 40 joules of energy the spring that went into the spring are no longer part of the system. All right, so those 40 joules that it absorbed left the system, and therefore the mechanical energy of the system went down by 40, and this is now an open system because the spring was not part of the system. Let's go back to that earth clay ball. Okay, remember we had that earth clay ball, and we're talking about, I want to show between when it's released and the moment before it hits the ground. So we did this before. So we said 25, 50, 75, there's 100 joules of gravitational potential energy that gets converted into 100 joules worth of kinetic energy. This is a closed system at this point. There's a conservative force, gravitation, acting between two objects which are both part of my system, the earth and the clay ball. But let's take a look at what happens when the clay ball hits the ground. When it hits the ground, it just goes, and its kinetic energy goes to 0, and its gravitational energy goes to 0. So its mechanical energy goes to 0. What's going on here? Well, okay, so now I have an open system because my mechanical energy went from 100 to 0. Basically, what happened is the atoms in the clay ball are now moving with 100 joules worth of thermal energy. The truth is, some of it also went into the ground, but I'm not thinking about that when I drew this one here. Okay. Let's get. Was that the last one I had? That's it. We're done. Thanks for watching.